66 million years ago, a 10-kilometer rock barreled toward the Yucatan Peninsula. But in this timeline, orbital mechanics slightly shift. The asteroid clips the upper atmosphere and ricochets back into deep space. There is no impact equivalent to 10 billion atomic bombs, no global firestorms, no ash cloud blocking out the sun and halting photosynthesis. The Earth keeps turning, entirely unharmed. Non-avian dinosaurs, pterosaurs, and massive marine reptiles glide right past the Cretaceous-Paleogene boundary. The ecosystems they dominate remain fully intact and operational. Without a sudden cosmic intervention, the planet's apex species are left alone to face a much slower, more grueling test. Over the next 66 million years, they will have to survive the extreme continental fracturing and dramatic climate cooling of the Cenozoic era. To understand how they weather these changes, we have to look at the state of dinosaur life right before the asteroid missed. For decades, a persistent paleontological myth suggested dinosaurs were already staggering toward extinction anyway. Recent ecological niche models correct for preservation biases in the fossil record and show the exact opposite. Dinosaurs were highly adaptable, rapidly diversifying, and easily surviving the climate fluctuations of the late Cretaceous. Paleobiological data shows a bifurcation in how these animals processed energy. The massive sauropods and two-legged theropods operated with high-energy, warm-blooded metabolisms. Meanwhile, the horned and armored ornithischians maintained lower-energy, cold-blooded strategies. This metabolic divergence provided two distinct paths for survival. High-metabolism saurischians could colonize cold, seasonal latitudes by maintaining internal heat, while low-energy ornithischians required fewer calories to survive, allowing them to endure resource-scarce environments through seasonal migrations. Together, these strategies allowed dinosaurs to saturate every available climate on a cooling planet. 14 million years ago, the Miocene epoch brought severe global cooling. The lush tropical forests dried out and gave way to vast arid expanses of early savanna. This new landscape presented a major biological hurdle. Grass is laced with microscopic, glass-like particles called silica phytoliths. Eating it is like chewing on sandpaper. It rapidly grinds down normal teeth to the nerve. This chart shows the internal structure of a hadrosaur jaw. To consume this abrasive food source, they perfected a dental battery of continuously migrating teeth. Each tooth floats in a dynamic ligament, cushioning the immense mechanical stress of grinding grass. Out on the plains of Africa and Asia, massive titanosaur sauropods adapted by abandoning the high tree canopies. They evolved broad, flat beaks perfectly shaped for scything grass and developed heavy, fat-storing dorsal sails along their backs to survive seasonal droughts. By evolving highly specialized jaws and extreme drought tolerance, these heavyweight herbivores quickly locked down the open plains. They consumed the available resources so thoroughly that no other group of animals could carve out a space at the top of the food chain. Which brings us to the mammals. With 66 million years of unbroken evolutionary time, why did our ancestors remain trapped in the underbrush, never growing larger than a rodent? This diagram illustrates a critical reproductive divide. Dinosaurs lay large clutches of small eggs, producing fast-growing offspring at low cost. Mammals rely on long internal gestation, investing massive energy into a single fetus. This makes them slow and physically vulnerable. This reproductive bottleneck forced mammals to hide, evading the constant predatory pressure. They had to stay very small, become strictly nocturnal, and live underground, biologically capping their body mass at under 100 grams. 2.6 million years ago, global temperatures dropped significantly enough to trigger the Pleistocene glaciations. Massive continental glaciers expanded, burying temperate forests and bringing months of total winter darkness. To endure the freezing tundra, apex predators grew thick, multi-layered coats of shaggy feathers. This dense insulation retained their high metabolic heat while shifting to stark white in the winter for camouflage against the snow. But insulation wasn't enough. Exposed extremities lose heat quickly and are highly susceptible to tissue necrosis. To prevent frostbite, these Arctic tyrannosaurs entirely lost their forelimbs, streamlining their bodies to trap maximum warmth. From the arid expanses of the Miocene to the brutal ice fields of the Pleistocene, dinosaur physiology adapted to every extreme. They survived the deep freeze, locking in their absolute rule over the biosphere. In a modern era where dinosaurs still walk the Earth, focus heavily shifts toward brain evolution. Given 66 million years of extra time, a lineage of theropods would encounter the same cognitive pressures that drove primates toward tool use. In 1982, paleontologist Dale Russell proposed the Dinosauroid. He hypothesized that a big-brained dinosaur would inevitably evolve to look exactly like us, adopting an upright, tailless posture and a flat, human-like face. Today, modern paleontology rejects this idea completely. Assuming that the human body plan is the ultimate required shape for intelligence is scientifically flawed. A highly intelligent theropod would keep what works. It would maintain a stable horizontal posture, using a long muscular tail for balance. For complex tool manipulation, it would combine a highly sensitive crow-like beak with dexterous three-fingered claws. Intelligence doesn't require erasing millions of years of successful anatomy. Instead, advanced cognition simply layers on top of the highly efficient feathered body plan that already conquered the planet. The existence of an intelligent dinosaur forces a reassessment of evolutionary progress. It challenges the assumption that the human form is an inevitable consequence of increasing brain size. In this timeline, it is a feathered, egg-laying creature quietly looking up at the stars and pondering its own existence, while our small mammalian ancestors are still scurrying in the mud, forever hiding from the light of day. Our presence here isn't some biological destiny. The fact that humans walk the Earth today is simply the statistical luck of a space rock hitting the Yucatan Peninsula exactly when it did.